thing I have written down for alkynes is just knowing which alkyne is a stronger or weaker acid. Is that basically all that we're gonna be
Well,
focusing on, is just determine, like, we drew 2 different alkynes, just to know?
you need to know about hybridization. You do need to know about the special acidity of terminal alkynes. Is this a terminal alkyne or not?
No.
No, it's internal, right? And then there's no hydrogens attached to this
It
carbon.
has to be SP, right?
These are SP hybridized. That's right.
No, I mean, it has to be, because there was a degree, like, it has to be attached to just one. It has to be SP3 for it to be, it says something about it in the book.
To be acidic?
Yeah, it was like there can be 3 of them, and it's like degree 1, degree 2, degree 3, but you can only use the only acidic one is the one that's attached with one bond, so the SP one, because it has 50% S. Am I making sense? I might be saying that wrong, but it's,
Maybe, I think you're maybe
I
getting
thought
a couple.
that was just determining the acidity of,
This hydrogen is acidic in a terminal alkyne. And it's more acidic than an alkene that has hydrogens, which is a lot more acidic than if it was just an alkane.
and that's SP3 hybridized, right?
Oh, this is SP.
It's, yeah, okay, then that's what I was saying. SP, only the SP ones can be terminal acidic ones. If it was SP2, then
They're acidic as well, but not as
it's
acidic.
not as acidic, so you wouldn't use it. That's what it said in the book.
Wouldn't use them. I don't know what that piece means, wouldn't use it, but,
I'll find it.
so the pKa of this is about 25. The pKa of these hydrogens is about 44. And the pKa of just an alkane, we'll just put methane up here, is about 50.
so something you would ask would be more along the lines of which group is more acidic, or which one has the most acidic hydrogens? So
I could ask it both ways. I could say, of these molecules, which one has the most acidic
you already
hydrogens?
know that
Then you'd pick that one.
alkynes are
Yeah.
more acidic than alkanes.
Yeah.
And it just kind of goes down.
And then if I asked you, what effect is responsible for this being more acidic, what would you say?
It's SP.
The SP or.
Well, we call it the hybridization effect, but yes, that's right.
So I found it in the book. It says the more S character in a hybrid orbital of a carbon, the more electronegative the carbon will be, resulting in a greater stability of the anion and thus more acidic hydrogen. Of the 3 types of organic molecules, the series alkene, alkyne, alkene, and alkane, the carbon in an alkyne, sp hybridized, 50% S character, is the most electronegative. Therefore, an alkyne anion is the most stable of the series, and the alkyne is the strongest acid of the series. And so it says in the bottom that only this hydrogen is acidic enough to be deprotonated by NaNH2.
Well, yeah, but you would have to have given me the base to say that comment. I can deprotonate these, but I can't do it with NaNH2. I can actually deprotonate these, but I can't do it with NaNH2. I have to have a stronger base than this to do that chemistry, and that's hard to do. But that's beyond the scope of this course. Yeah.
Do you think you could go over how to read a Newman projection? Because I think I know how, and then I second guess myself. Now you can do it again.
What do you mean by read a Newman projection?
Like the circle, because I thought she doesn't, I don't know, like for a big circle, that's just a line, that's just carbon, right, the big one?
It represents a carbon atom.
Yeah, and
That's-
the middle one is also a carbon.
It is.
Okay.
So remember, you're looking down a carbon-carbon bond, right? So, if, you know, the example in the book is butane, right? So if we're going to take our eyes and look down this bond, what would we see? So if this is the carbon and this is the carbon, and I look down that bond, what do I see? I see a carbon that's towards me, and I see a carbon that's away from me, right? And we have to be able to represent that on a 2-dimensional surface. So if I took a flashlight and put it up here and I projected this, all I would see is one circle with things hanging off of it, right? Well, that doesn't help me much. So I've got to have a way of representing that. And the way that we do that is we represent the back circle or the back carbon as a circle. So this is where my eyeball is, so this would be the back carbon, right? So it's going to be represented as a circle. All right, well, what's attached to it? A CH3 and 2 hydrogens. Right? So that's the back circle, or the back carbon represented as a circle. Now the bond between that back carbon and the front carbon I can't see because I'm looking down that bond, right? So all I got to do is put a dot in the front. And I know that that dot means that that carbon atom is bound to that back carbon atom. Right? Well, what's attached to this front carbon?
Same thing.
2 hydrogens and a methyl group, right? And notice that they're 180 degrees from one another. So I got to draw it straight down.
Yeah, I just want to make sure that was what I was doing.
Yep. Have you all looked at the practice or the old exam? Okay.
I did, but I felt like none of the questions had anything to do with what we were.
Well, there's some of the questions at the very beginning. Remember the introductory material we talked about the first day where we talked about periodic trends, we talked about electron configurations a little bit, we talked a little bit about orbitals.
The first couple questions actually was asking like, I want to say, history. Like
We talked about that the first day of class. You know, I talked about,
I don't have any of that written down. I don't-
that's in that introductory slides that we talked about the first day.
I do have it.
Wait, are you gonna ask us like history questions? Like who named blah blah, or who, the name of the guy?
Things that I put on those first days of lecture notes that introduced the course are fair game as well. So we talked about Kekulé and Frederick Wohler and father of organic chemistry a little bit. We talked a little bit about medicines and dyes and why organic chemistry was important. We talked a little bit about that. That's fair questions.
How many questions like that?
I'm not going to answer that question.
Because that will determine how many I miss. I don't know.
Well, you've got now until Monday to go back and look it over.
So is this like a multiple choice, or
Yeah,
is there like
I
a mix of multiple choice and like workout problems like that?
There are problems that you're going to have to work out, but I'm not going to grade your work. I'm going to grade what you pick up. So every question is multiple choice.
Oh, and there's also no partial credit for the work, because you're not grading the work. No.
Wait, you said if we had the right answer written down, but we circled the wrong thing or something, that you'd give it to
Well,
us?
that's not partial credit though.
Oh.
That's going back and just saying, oh, I did write down the right one, I just selected the wrong one. I'll give you credit for that.
Okay, so in alkenes.
If I catch it,
Okay.
or if you catch it, let me know.
What,
Repeat that?
for the alkenes,
Yeah.
I have written down like mono, substituted and di.
Mono, substituted, disubstituted, trisubstituted.
Substituted?
Substituted, yeah. How many things?
I wrote it, spelled it.
All you do
Spelled it in a different word.
is look at the carbon-carbon double bond and ask yourself what's attached to it. So you look at the carbon-carbon bond. How many carbons do I have attached to that alkene? I have 2, so this is a disubstituted alkene.
So it's. Oh, okay, okay.
Because that's 2 R groups.
Okay.
Okay, what about,
How would you, I'm sorry.
Sorry.
can I just-
Go ahead.
How would you ask the question with that? What kind of question
Oh.
do you expect to see?
I mean, something like that, I could ask a question like you just asked it, right? Identify this alkene, and I could write, A, B, C, D, monosubstitute, disubstitute, trisubstituted, tetrasubstituted.
Okay, so you don't have to throw that into the nomenclature of like
No.
anywhere.
No, when you start to have di-substituted, tri-substituted, and tetra-substituted, you start to have E and Z, usually, right? And
Right.
so that's where that comes from.
How do you name a tri-substituted or tetra-substituted whenever?
Ours don't have to be the same, remember?
Right.
So let's say we have a tri-substituted alkene. And let's say it's this. That is a tri-substituted alkene.
Why? Because of the,
When I look at this, I've got R, R, and R. So there are 3 R groups attached to the alkene, so it's tri-substituted.
so you don't count the H as an R group, right?
No. H is a hydrogen.
Okay, so I thought you were going off of the one side because, you know, the last one you just did, whenever it was a di-substituted, you had an H and then an R. Did you have an R and an H?
Yeah.
Just 2? So you go off the overall
Yeah,
alkene,
what overall is attached to the alkene.
not just one carbon.
That's right. Well, tri-substituted, you have to have 2 groups, at least on one of the carbons, because I can't put 3 substituents on one carbon.
Right. And
But, for example, a di-substituted could be this, or it can be this. Both of those are di-substituted alkenes.
It's about the carbons, not the hydrogens.
right, well, yeah. Okay, and then how do you, an R,
Carbons or whatever the R group is.
the R group can R group be anything other than H?
Anything other than hydrogen.
So anything at all, iodine, fluorine?
Yeah, it could be. For this exam,
Oxygen.
I will probably, if I use R, interpret it to be carbon.
Okay, and then,
I don't know that I've
so
done
how
that.
do you do, tetra-substituted? Is it just all R's all the way around? Okay. Gotcha.
Don't forget, we also started talking about some reactions. So addition reactions are also going to be fair game for alkenes.
Can we do that?
Can we do that?
5.
So let's just start by talking about, tell me. So what kind of reactions do alkenes like to do?
Additional.
Addition reactions, right? And up to this point, what have we learned that we can add to an alkene?
HCl.
We can add HX, where X is Cl, Br, or I. Where X is equal to Cl, Br, or I. And we can do that, right? Okay, very good. What else can we add?
X2.
We can add X2.
What?
Where X is what?
What was it, like bromine and fluorine?
Chlorine and bromine, no iodine in this case. We haven't really learned why that's the case yet, but that would be fair game. And then we talked about adding water. We talked about the fact we need a little acid so we can add water across a carbon-carbon double bond.
Those are the only ones we talked about, right?
Those are the only ones we talked about. And of the ones that we talked about this the most. We even started talking about the mechanism of this a little bit. Right? We pushed some arrows on the board. We talked about how it is a 2-step process that hydrogen gets attached to the carbon with the most hydrogens, right? We talked about Markovnikov's rule. We have not talked about addition to alkynes yet, so don't worry about that.
Okay, I have a question about the diagram. So one of the questions said sketch an energy diagram for a 2-step reaction that is endothermic in the first step, exothermic in the second step, and exothermic overall.
Okay.
How many transition states are present in this two-step reaction? How many intermediates are present?
Very good question.
So,
So when we do this, we're going to have energy on the y-axis, right?
yes.
We're going to have reaction coordinate on the x-axis. And it said, right, that we're going to start somewhere with our starting materials,
Yep.
and then we're going to end up with products that are lower in energy than our starting
That's our
materials.
final.
And how do we know that? We know that because it said the process has to overall be exothermic,
Exothermic.
which means my reactants have to be higher energy than my products.
Yes.
So I already know that.
And then it was 2 steps, so there's gonna be a little loop.
Okay, so we go up, and it's going to be endothermic in the first step.
Endothermic in the first one. So not past that line.
Okay.
And then exothermic in the second one and exothermic overall.
We've already taken care of the exothermic overall.
Exactly, so just do another one that's less than that one.
Yep.
Okay. And then,
So here to here is the energy of activation in the first step. This is the transition state. This is a
intermediate.
intermediate. I think I spelled that right.
Yeah.
This is the energy of activation for the second step. And my E's, EA2, right? And it's slightly endothermic, but overall
Exothermic.
exothermic.
So my question, well, that's exactly what I got, but it said to identify the transition states and the intermediate. So there are obviously 2 transition states, but for the intermediate, what threw me off with it is it said intermediate, and I didn't know that you could have more than one intermediate. If it's because an intermediate is the lowest point between 2 transition states, so that's just one,
For
right?
a two-step process, you can only have one intermediate.
For a 2, okay, that's what I wrote. I thought, like, I didn't know if it was,
But I could show you some reactions that actually go through 4 or 5 steps.
but that would have to look like that.
It would have
have
multiple
multiple
transition states,
transition
multiple intermediates, that's right. And an intermediate rests between 2 transition states, that's right.
Also, there was another question right after it, and it asked about, it was true and false. And it said an endothermic reaction cannot have more than one intermediate. And I said, that's false. Because it can. It just depends on how many little loops it has, right?
An endothermic reaction is about this, the overall. Right, I could have drawn this, well, no, let's leave that alone. Let's leave that there.
You could have just added more intermediates.
Let's say the product is here. That overall would be an endothermic reaction with 2 transition states and an intermediate.
Yes. But the question asks, it says, an endothermic reaction cannot have more than one intermediate. I said it was false.
It is false. I could draw another
Okay.
step in there as well.
And the same goes for
Endothermic overall just depends on where your starting material and the products are. Doesn't matter about what's in between. So, I mean, for it to be that definitive, it makes it false.
Exactly. And it also, there was another one that said the transition state can never be lower in energy than the reactants, and that's obviously true because the transition state is the maximum, right?
You cannot have a negative energy transition state.
Yeah.
That's right.
So it's, I just mentioned.
The transition state is moving on to something, and if it was going in the opposite direction, that just doesn't make any sense.
Yeah. We didn't really talk much about it, so I wanted to make sure, but that's what I got.
So you're saying seeing a coordinate like that is, you call that overall endothermic?
Yeah, because my products are higher in energy than my reactants.
Okay, so whenever it falls past it, it's just exothermic overall?
Well, when it goes from starting to product like that, that's an exothermic
Right.
reaction.
Yeah, finishes it
Mhm.
from the start. Okay.
Which is what most reactions are in organic chemistry. Most of them are exothermic reactions. But this is an endothermic step. To go from here to here is endothermic.
Right.
To go from here to here is endothermic, but to go from here to here is exothermic. Right? To go from here to here is exothermic, but to go from here to here,
Can you really have a endothermic, did you say the first one's endothermic, right?
to go from here, an intermediate is a product, right? It just
Right.
doesn't live very long. So to go from here to here is overall endothermic.
So can you have that first one be exothermic and then go back to an, endothermic?
That would get to what she's talking about. the first step usually is never, that I can think of, exothermic.
Well, no. So from start to the first transition
That's,
state,
that's endothermic?
endothermic. But the next one down, where you said, can you have that be exothermic and then come back up to another transition state, or once it? I don't know if I'm
Yeah, I'm not understanding.
yeah, I don't know how to say what I'm
I
thinking.
think you're making it more complicated than you need.
Probably. Didn't do that sometimes.
Focus on this.
Okay. Yeah, here, it was something about what y'all were talking about, it's just, something you said, but I don't know how to put it in words.
What else? Got 4 minutes.
Would you ask us a question like about molecules, like have us think, okay, like 4.35 for example. It asks, like it says blah 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 is solid at room temperature and is, but I know which one is trans and which one is cis, because the one that's trans would be the one that's solid at room temperature. But is that what the answer is? Like I didn't know what kind of answer you were looking for.
So, if you read the book, trans fatty acids, right, trans fats, if you will, typically at room temperature are solids. And it's because of their shape. They have van der Waals interactions that are very favorable. They can get close together, they can pack. We didn't talk about that in class much. I did talk about some of it. The fact that they can interact with one another and pack is why you end up with the solid structure. If you start to put in double bonds, think of those as like kinks that don't allow things to get very close together and pack very well, and so that they remain liquid. They don't interact with each other as well as the trans.
So like hydrogenated vegetable.
Well, hydrogenated is actually saturated, and we know that saturated fats are typically solids at room temperature as well.
Right. So which one? Would you answer the question?
So what is the
The question from the book. Okay, I'll read it. It says oleic acid and ileate, I don't know how to pronounce that, acid are respectively the cis and trans isomers of 9-octadecanoic acid. One of these fatty acids is a colorless liquid that solidifies at 4 degrees Celsius, is a major component of butterfat. The other is white solid and melting point of 44 to 45 degrees Celsius. It's a major component of partially hydrogenated vegetable oils. Which of these two fatty acids is cis isomer and which is a trans
The
isomer?
trans isomer is going to be one that has the higher melting point.
Okay.
So the one that, yeah. Now, you all know that if you go and buy olive oil, right, on the shelf at room temperature, it's a liquid. What happens to it when you take it home and put it in the refrigerator?
It's slightly solid.
Yeah, it gets slightly solidifies, right? And so cis alkenes will form solids. You have to get them cold to do that. Whereas when you buy, I don't know, coconut oil or whatever that comes solid at room temperature, it has a different melting point. So usually, and you have to remember, we got to be talking about the same number of carbons. Right? And that's why it said it's the same molecule, just the difference in cis and trans. I can put a lot of carbons on a cis double bond and make it solid at room temperature. But you always got to be talking about the same number of carbons, same number of hydrogen, same functional groups. Yep, you got it. Final question. All right.
Okay, wait.
Go ahead.
I'm sorry, I have a lot of questions, but we talked about going from molecular structure to a line one. Are you gonna ask us to do the opposite? Because one of the questions asked me to do the opposite, and it kind of really like confused me. Like going from the name to a not line structured, but to the writing it down, like molecular condensed.
I like bond line structures, so I think just about everything I've got on the exam is a bond line.
Okay, so you wouldn't ask us to do the other way around.
It's not that it's not fair game, I just can't, I don't think I did.
Okay.
But I won't swear to it, I don't know all of my 25 questions off the top of my head.
Okay. Because like I feel like we don't really use that. Like we learn it first, but then we don't usually go back to doing that. And it
should
really
go bond
confused
line.
me when it asked me to do that.
Bond line's the easiest way to drive it.
Yeah.
You said you don't know the answers for this, do you?
I don't have the answers.
Don't have the answers, that's what.
I do know the answers.
I'm
But
saying
I
you
have to do
can't-
the exam. But I don't have the answer sheet.
Sorry.
Well, thanks for coming out on a football game day. I will post this on YouTube probably after lunch, make it available to you all. Relax.
This is right. I can't find the answers to most of these questions, so I do
Miss,
them.
I don't
and
know
I'll
shit over
the
here.
better ones.
Wait, talk?
I just heard her talk, that's all I keep
You're always going to want a number such that you give everything the lowest possible number. 1, 2, 3, 4, 5, 6. If you numbered the other way, it'd be 1, 2, 3, 4, 5, 6. And so I think you're right. I think that's going to give it, right? So this is a cyclohexene.
Yes.
And when we're talking about a cyclohexene, your carbon and the alkene is always going to be 1, but we could go ahead and write that in anyway. That's fine. What are our substituents?
We have a trimethyl right here, and then
Okay.
we have a terbutyl.
All right. So B for butyl comes before M in methyl,
Yes.
right? So it's going to be 1
One terbutyl,
butyl,
and it's this part that I wasn't sure. I wrote 2,4,4 trimethyl.
2,4,4 trimethyl.
Cyclohexene. I didn't write the one though because that's
Yeah,
implied.
it's implied. If you had written it, I wouldn't have counted it wrong. That's the name.
Awesome, so I did get it right.
Looks to me. Yep, good deal. Okay. Bye. I got all this stuff all over my hands.